Hi all. Today we discuss the matrix representation of linear transformation. Let T be a linear transformation from a vector space V to W. Both are defined over a field, a common field F. And if you fix two bases B and B prime, B is a basis for V and B prime is a basis for W. Uh, this B consists of the vectors, say alpha 1, etc., alpha n, and B prime consists of the vectors beta 1, beta 2, etc., beta m. So these are two bases, two ordered bases. B and B prime are two ordered bases. Two ordered bases. So corresponding to these two bases, ordered bases, we can define a matrix corresponding to this T. First, we write this T alpha 1. Of course, this T alpha 1 is an element of W and B prime is a basis for W. Then T alpha 1 can be expressed as a linear combination of this beta 1, beta 2, etc., beta m. So we write T alpha 1 as some A11 beta 1 plus etc. AM1 beta m, or we write this as I equal to 1 to m aij, this is ai1 beta I. Similarly, we write T alpha 2. T alpha 2 is again an element of W and B prime is a basis. Then we write this as A12 beta 1 plus A22 beta 2 plus etc. AM2 beta m. That is equal to summation I equal to 1 to m ai2 beta I. Similarly, you can write T alpha n. T alpha n is equal to a1 n beta 1 plus etc. amn beta m. That is summation I equal to 1 to m ai n beta I. So we can write this these n equations as T alpha j as is equal to summation I equal to 1 to n aij beta I. So when you put j is equal to 1, you can get the first equation. So this j varies over 1 to n. Okay, so these equations defines a set of coefficients, set of mn coefficients aij. So this defines a matrix called A, which is equal to the matrix aij of order m by n. Okay, so this matrix is called the matrix relative to this A is called the matrix. A is the matrix of T, matrix of T relative to the basis, B and B prime, relative to the ordered basis B and B prime. So this is the definition of a matrix corresponding to a T if we are fixing B and B as ordered basis of V and W respectively. Now we explore the relation between the matrix A and T. Okay, so once you take any alpha belongs to V, then this alpha can be expressed as x1 alpha 1 plus etc. xn alpha n. Our assumption is B contains the vectors, it's a basis of V containing the vectors alpha 1, alpha 2, etc. alpha n, and B prime is the set of vectors beta 1, etc. beta m. These are basis for V and W respectively. So this is subset of V and this is the subset of W. And if you take any arbitrary element alpha belongs to V, you can write alpha as a linear combination of these alpha 1, alpha 2, etc. alpha n. Now you write T alpha is equal to T of, you can write it as summation I equal to 1 to, or j is equal to 1 to n x j alpha j. Okay, so this is the abbreviation of this, or summation formula for this right side. So that is equal to summation j is equal to 1 to n xj t of xj alpha j, since t is linear, so you can write it as t xj t alpha j. And we know that t alpha j can be expressed as this expression, t alpha j is equal to summation I equal to 1 to n aij beta I. Now you write this is equal to summation j is equal to 1 to n xj summation I equal to 1 to m. This t alpha j can be replaced by this formula aij beta I. Since this j is this xj does not depend on this I, you can write this as j equal to 1 to n and summation I equal to 1 to m xj or aij xj beta I. Now you can replace interchange the order of summation because it contains only a finite number of terms. So the order of summation results the order of the elements, in the order of the element we have added aij's. So that is equal to summation I equal to 1 to m summation j is equal to 1 to n. So when you write interchange, when you interchange these two summation, you can expect the sum is not changed. So that is equal to aij xj beta I. Now this beta is independent of j, then you can take this beta I out from the inner summation. So that is summation I equal to 1 to m and summation j equal to 1 to n aij xj times beta I. Okay, so this is the expression of t alpha. Any t alpha can be expressed as a linear combination of this beta i's. Yes, if you start with alpha from V, you can get T alpha. The corresponding T alpha is in W, and that can be expressed as a linear combination of beta I involving some coefficients. So these coefficients are called the coordinates of this T alpha with respect to B prime. Okay, so when you write this coordinate of T alpha with respect to B prime, that is nothing but the summation j is equal to, this can be written as for I is equal to 1, you can get the first entry, and I is equal to 2, you can get the second entry. So j is equal to 1 to n a1j xj is the first entry of the, or that is the first coefficient when I is equal to 1, and the second coefficient is sigma j equal to 1 to n a2j xj etc. The last one will be summation j equal to 1 to n amj. This beta is up to I equal to 1 to n, so amj xj. Okay, so this is the coordinates of t alpha relative to the basis b prime. Okay, now you write this is equal to this can be expressed as, and this can be written as the matrix. The first row will be a11 x1. When you expand this, the first summation a11 x1, then j is equal to 2, then you can get plus a12 x2 plus etc. a1n xn is the first row, the first entry of the first row. It has only one entry in the first row. The second entry will be it's a column matrix, so it's a code. These are the coordinates. So the second entry will be 21 x1 plus a22 x2 plus etc. a2n xn, and the final entry will be am1 x1 plus etc. amn xn. Now you can write this as the matrix A times, so this is the matrix and this is our x1 etc. xn. So this matrix can be written as A11, A12, etc. A1n, A21, A22, A2n, etc. The last will be AM1, AM2, etc. AM. So this is the product. This can be written as A times this x1 x2 xn comes from this expression. So any alpha belongs to V can be expressed as this form. Then this x1 x2 xn constitute the coordinates of alpha relative to the basis B. So you can write that can be represented by the coordinate of alpha relative to the basis B, and this the coordinate of alpha with respect to relative to the basis B prime. So that is T alpha, the coordinates of T alpha corresponding to relative to B prime. So this is the relation between the matrix and the linear transformation. If you define the linear transformation, if you have a linear transformation and corresponding to the linear transformation, you can define a matrix relative to two-ordered basis B and B prime, then that satisfies this equation. Okay, so T is represented by the matrix A in this manner. Then what is the relation between T and A? Then any alpha you can write the coordinate of T alpha relative to the basis B prime can be obtained by multiplying the coordinates of alpha relative to B. So this is the relation between the matrix and the linear transformation and the matrix representation of the linear transformation. The interesting facts on the matrix representation is if you have two linear transformation T and U from this V to W, we have two different linear transformation. Then corresponding to T there is a matrix A, and corresponding to U there is a matrix B. Okay, if we fix an ordered two ordered basis B consists of vectors alpha 1 etc. alpha n is a basis for V, and B prime that consists of the vectors beta 1 etc. beta m subset of W. Then corresponding to T there is a matrix A, and this is defined by the equation T alpha j is equal to summation I equal to 1 to m aij beta I, and the matrix B is represented by obtained by U alpha j by the equation U alpha j, that is equal to I equal to 1 to m bij beta I. So these are the relation between these two transformations and corresponding matrices. Now you define T plus U using the algebra of linear transformation. You can define T plus U. Then how do you find the matrix of T plus U? So that is the idea here. When you write T plus U, in order to find the matrix of T plus U, you need to evaluate a T plus U of alpha j. Then that can be written as T alpha j plus U alpha j, and correspondingly you can write it as I equal to 1 to m this aij plus bij times beta I. Okay, so this defines the matrix of T plus U. That is, the matrix of T plus U is represented relative to the basis B, and B prime is related by this formula. That means here the A is A can be denoted as the matrix of T relative to the basis B and B prime. Similarly, the matrix of U, that is B, is denoted by the matrix of U relative to the basis B and B prime. Now the matrix of T plus U relative to the basis B and B prime can be denoted in this notation. Then that is nothing but Aij, the matrix Aij plus Bij. Okay, and this can be written as matrix Aij plus the matrix Bij. Okay, so this is equal to the matrix of T relative to the basis B and B prime, and that is the next will be the matrix of U relative to the basis B and B prime. Okay, similarly you can define the matrix of CT. The matrix of CT relative to the basis B and B prime can be obtained by evaluating CT of alpha j. CT of alpha j is nothing but C times T alpha j is nothing but summation I equal to I equal to 1 to n 1 to m aij beta I. Then this can be written as summation I equal to 1 to n 1 to m C times aij beta I. Then this defines the matrix of CT. Okay, so the matrix of CT is the matrix C times aij, and that can be written as C times the matrix aij, and that is equal to C times the matrix of T relative to the basis B. So these two results implies that when you take T and U, then the matrix of CT plus U relative to the basis B and B prime is nothing but C times the matrix of T related to the basis B and B prime plus matrix of U to the related to the basis B and B prime. So this would enable us to define an isomorphism between the linear transformations and set of all M-bind matrices over F. Of course, these AIJs are elements of the corresponding field. If V and W defined over a common field F, then these coefficients, these are the scalars, these are the coefficients or coordinates of these T alpha j and U alpha j. All these coefficients come from the common field F. So we will next we will define an isomorphism between a set of all linear transformation from V to W, that is denoted by LVW, and we will prove that that is isomorphic to F m by n. So this is the vector space of all m by n matrices.